Hey, let's talk about intermolecular forces. So we're talking about two questions here. What holds atoms together versus what holds molecules together? So we've talked a lot about what holds atoms together. Bonds. Bonds are like the glue between atoms. And we can also call these intramolecular forces because they are within a molecule. But what we're going to talk about today is something we haven't talked as much about, which is the forces that hold entire molecules together. Those are intermolecular forces because they are between entire molecules. And because a picture says 1,000 words, this is an amazing picture. So it's showing the bonds are between the oxygen and the hydrogen, and the intermolecular forces are between entire water molecules. So it's a lot easier, as you would probably guess, to break an intermolecular force versus breaking a bond. And what I mean by that is it doesn't take as much energy to break an intermolecular force as it does a bond. So, always a good question. Why do we care about this? Well, we care because if we understand intermolecular forces, it can really help us understand the different properties that molecules have, like their melting point, their boiling point, how quickly they evaporate. The surface tension of water is such a special characteristic, and it can be explained by intermolecular forces. It can explain things like why water boils at 100 degrees and yet oxygen is a gas at room temperature, meaning it has a much lower boiling point. Okay, so intermolecular forces are also seen as IMFs or IM forces. They all mean the same thing. Again, these are the forces that hold molecules together, and they depend on what type of molecule you have. So if a molecule is nonpolar, it has dispersion forces. If a molecule is polar, but it's not superpolar, it has dipole-dipole forces and dispersion forces. And if something is superpolar, it has hydrogen bonding forces. They're so strong, they're named after a bond, even though they're just a force. And things with hydrogen bonding forces also have dipole-dipole and dispersion forces as well. So just like I mentioned, there are three types of intermolecular forces. The weakest are dispersion, and they're sometimes called van der Waals. Dipole-dipole are medium strength forces, and hydrogen bonding forces are the strongest. Okay, I like to have pictures. So here we've got strong hydrogen bonding, middle dipole-dipole, and weak dispersion forces. Okay, then again, we've got strong hydrogen bonding forces, middle strength dipole-dipole forces, and weak dispersion forces. Okay, so let's start with the weakest. These forces exist in all molecules because there's always random motion of electrons. So what can happen is the electrons moving around all of a sudden kind of gather on one side of a molecule, and they cause the electrons in a separate molecule to kind of repel away and therefore have a slight positive side near the slight negative side. And so there's this weak attraction. The larger the molecule is, the more likely this attraction will occur in that it will be stronger. So bigger molecules tend to have stronger dispersion forces than smaller molecules. So looking at an example here, oops, sorry, went too fast, of propane versus octane. You can see propane's just a little guy, C3H8, Octane is a big guy, C8H18. They're all carbons and hydrogens, so these are non-metals and they're non-polar because carbon and hydrogen have an electronegativity difference less than 0.5. So propane is a lot easier to boil than octane because the forces between propane molecules are much weaker, so they're easier to break. It takes less energy to break those bonds. Okay, and again, I'm talking about the forces between entire molecules. So if I draw C3H8, just to really show you what I'm talking about here, there is a slight attraction to another C3H8. Okay, I'm just going to depict this with a little heart. Okay. And then if we've got C8, this is going to take a while to draw 4, 5, 6, 7, 8. Pretend I drew all the hydrogens on here, okay? And then we've got another C8H18. You can see already it's got a lot more surface area where it can interact with the other molecule, and that's the key there. So here it's got, another attraction. It's got attractions all over the place. I'm going to draw a big heart. So it's harder to break the intermolecular forces between the octane molecules than it is to just break this. Boom. Even isomers of the same formula can have different intermolecular forces, and I alluded to this when I discussed surface area. So if I had another molecule of this type, another sphere molecule right here, okay, versus another molecule of this type right below it, you can see that this one has a lot more surface area where the two can interact versus here it's just a little bit. So this second one is going to have stronger intermolecular forces, again, because of that increased surface area between the two. And you can see the boiling point is 35 degrees, and this one, it's only 9.5. So it's easier to break this intermolecular than this one. Dipole-dipole forces are stronger than dispersion forces. This is because we're talking about polar molecules. So rather than depending on this like electron motion to create these little pockets of partial negative and partial positive charges, the molecule already has an established partial negative and partial positive side. And so the partial negative side of one molecule is attracted to the partial positive side of another molecule. And so this is why it's a stronger attraction. And yet it's still weaker than hydrogen bonding forces. So these are superpolar because it's a hydrogen bonded to an F, an O, or an N. Okay, and in these cases, based on the number of bonds that they can form, like oxygen can form 2 bonds with maybe a carbon or another hydrogen, nitrogen can form 3 bonds. So what you end up getting is these super big differences in partial negative and partial positive for hydrogens bonded to an N, an O, or an F. And so because they're super negative and super positive, they're really attracted to each other. Okay, so you can see this is called a hydrogen bonding force. Okay, sometimes shortened to hydrogen bond, but that's so confusing. Okay, again, this is a force we're talking about. It's just so strong they named it after a bond just to confuse poor students. Okay, so hydrogen bonding forces can only occur if you've got that hydrogen bonded to an F, an O, or an N directly. It can't be like a hydrogen bonded to a C and then bonded to an O. It has to be the H directly bonded to the O. Okay. So let's look at an example here. H2 has dispersion forces only, and it's got a very low boiling point. Okay, so that means it's really easy to boil. It doesn't take much energy. HBr has dipole-dipole forces, a higher boiling point, and then water, H2O, has hydrogen bonding forces, and that's why it's very difficult to boil. It takes so much energy to break those forces. So in summary, we've talked about 3 types of intermolecular forces. Dispersion forces, which are found in nonpolar molecules, dipole-dipole forces, which are stronger than dispersion but weaker than hydrogen bonding forces. Those are found in polar molecules, and hydrogen bonding forces are found in superpolar molecules that have oxygens bonded to an H, nitrogens bonded to an H, or hydrogens bonded to an F. I like to have a little helpful thing. Chemistry is fun, almost like fun. It's an H bonded to an F, an O, or an N. That's how you can remember it. And to answer one of the questions from the beginning, why do we care? And I made the case that it helps understand the world around you. This is why water is a liquid and oxygen is a gas. Water is polar, so the molecules are held tightly together by these hydrogen bonding forces. That's why it's a liquid at room temperature. Versus oxygen is nonpolar, so the molecules are only held weakly together, which means that it's a lot easier for them to break apart once they've got some energy. The intermolecular forces aren't strong enough to hold the molecules together, so they fly away from each other as a gas. Funny related story. One time I had a student who we were working with little drops of hexane, and hexane is nonpolar. And they spilled a bottle of it, and so it's a liquid, but they spilled it on the table. So there's a big puddle of it, and they turned around, they were getting paper towels, and then they came back, and all of a sudden they noticed the puddle was just gone. It had disappeared, and they were like shocked. They were like, did someone clean this up? And I'm like, no, it just evaporated, because since the molecules are nonpolar, they don't care about each other. So these forces between them can be easily broken and they can fly away from each other. Let's do a little practice being able to identify the strongest intermolecular force present. So the steps that you need, if you're given a type of molecule, you need to be able to draw the structure, think about the shape of it in 3 dimensions, explain that if it's polar or nonpolar, and then look to see if it is polar, go that extra step of does it have an H bonded to an F, an O, or an N. So let's do these examples. And I also want to point out that you've got this flow chart, which is really helpful as well to kind of guide you to which path you're going on. So I would definitely have that nearby you as you're working through these. So pause the video before you get to actually working on these examples. And then I'm going to go over the answer. So if you've unpaused, hopefully you've already worked on this on your own. F2O, just a refresher in drawing, oxygen is in group 6A, so it gets 6 valence electrons. Fluorine is in group 7A, so it gets 7 valence electrons. So we connect everything once. This is a bent shape. Fluorine is 3.98 on the electronegativity chart, and oxygen is 3.44. So if we do a little subtraction here, we can see that the difference is greater than 0.5. So that means that we're going to draw arrows pointing toward the F, because the F has a higher electronegativity. So it gets a partial negative charge on each fluorine, leaving the oxygen partially positive. So this is definitely a polar molecule. Now, once we know it's polar, we go that extra distance and we ask, does it have an H bonded to an F, an O, or an N? No. So that means the force, the intermolecular force between an OF2 and another OF2, because the partial positive on the oxygen would attract the partial negative on another molecule's fluorine. This would be the middle strength forces, dipole-dipole. Next, HCl. Let's see, HCl or Cl is 3.16 and H is 2.1. This is a linear shape. So if we do the math here, we've got a difference of 1.06, which means that yes, this is going to be polar, with the chlorine having the partial negative and the hydrogen having the partial positive. Polar. And so if we've got another HCl right next to it, so we've got the partial positive attracted to the partial negative of the other molecule. This does not have an H bonded to an F, an O, or an N. So it's another example of the middle strength forces called dipole-dipole. CO2, we've seen this one quite a few times. It's got a linear shape. Oxygen is 3.44, and so it is greedier than carbon's what is carbon again? 2.55. There we go. So one oxygen would pull in one direction and the other would pull in the other. So they would cancel out. So this is non-polar, which means that if it's nearby another carbon dioxide molecule, it's only going to have weak dispersion forces attracting them together. And that's again because there are electron clouds around these molecules, and so there can be a small buildup of a partial negative, which kind of pushes away some of the negativity in another molecule, creating a slight partial positive, and so there is an attraction there. H2O, very common. You see this one all over. You probably already know. Since oxygen is 3.44 and hydrogen is 2.1, it is very polar. Okay, the partial negative is on the oxygen and the partial positive is on the hydrogens. And then if we have another H2O molecule nearby, they're going to be very strongly attracted. Does it have an H bonded to an F, an O, or an N? Yes. So this is hydrogen bonding forces. CH4. The electronegativity difference between carbon 2.55 and hydrogen 2.1 is only 0.45, so it's very weak. And so that means that this is non-polar. And therefore, a nearby CH4 molecule would only be weakly attracted to another CH4 molecule. This would be dispersion forces. Last but not least, if we draw out CH2O, carbon's got 4 valence electrons, oxygen's got 6. So we've got a hydrogen and a hydrogen. So connect everything once and we can see we've got a carbon double bonded to an oxygen. Oxygen's 3.44 is much stronger than carbon's 2.55. And so there is a pull that oxygen has a partial negative, leaving carbon a partial positive. So this is definitely a polar molecule. Does it have an H bonded directly to an F, an O, or an N? No. People get confused because they're like, wait, it has an H and an O, but they have to be directly connected. This is an H bonded to a C bonded to an O. So if there's another molecule nearby, the partial positive of the carbon is going to be attracted to the partial negative of the oxygen. And this would be dipole-dipole forces as the strongest intermolecular force present. So there you go. It just takes a little bit of practice to get used to these forces.